10-minute physiology. In today's video, I'm going to try to explain to you how the GABA receptor works in under 10 minutes. So let's give it a go. So I would like to start off by first looking at the neuron. And what we're going to do is we're going to zoom in at the synaptic terminal. Now inside the synaptic terminal, we have vesicles packaged with GABA. And these vesicles are going to be stored in the active zones. Now in order to release GABA into the synapse, we have to have a signal. And the signal is going to start out with voltage-gated sodium channels. As action potentials propagate down the axon, voltage-gated sodium channels open, allowing sodium to flow into the cell. The sodium will then depolarize the synaptic terminal's membrane, which will open voltage-gated calcium channels, increasing the intracellular calcium level, which will therefore facilitate the fusion of the vesicle with the presynaptic membrane, releasing GABA into the synapse. Now, GABA can bind to a specific receptor on postsynaptic cells called the GABA receptor, and this is the GABA receptor. The GABA receptor is a pentameric ligand-gated ion channel. So in other words, it's made up of 5 subunits. Now, on the GABA receptor is 2 binding sites, and these binding sites are coupled to gates inside the pore of this channel. And when a GABA molecule or other agonist binds to the binding site, the gate will open, allowing current to flow through it. Now, the maximal amount of current that can flow through this channel will be achieved when 2 GABA molecules are bound to the receptor. So when we have 2 GABA molecules bound to the receptor, the channel will now be maximally open, and it will be facilitating the maximum amount of current that can flow through it. So it's important to realize that the ion that is going to be flowing through this channel is going to be chloride. And the direction that chloride will be moving in will depend upon the cell membrane potential of the cell. So therefore, the effect of the open GABA receptor on the cell is going to depend upon the membrane potential at which the cell is at. So in order to understand the effect of the open GABA receptor, we have to understand the relationship between current and membrane potential. So this is a graph that is going to summarize the results of an experiment that is investigating this. So this experiment is investigating how membrane potential will change the current moving through an open GABA receptor. Now what we're going to do is we're going to summarize the results of this experiment on this graph here. So let's take a look. Now, I first want to establish a couple of main points before we look at this data in more detail. The first thing is what current is. So current is the movement of positive charge. And by definition, a negative current is when positive charge moves into the cell, and a positive current is when positive charge moves out of the cell. So a negative current will cause a depolarization, and a positive current will cause a hyperpolarization. And what we see here on this graph is an important point. And the important point is this point, which is the reversal potential. The reversal potential is the cell membrane potential at which the outward current moving through an open channel is going to be equal to the inward current moving through an open channel. So therefore, the net current will be 0 at this reversal potential. And for the GABA receptor, the reversal potential is going to be negative 75 millivolts. Now what we see from the results of this experiment is that when the cell membrane potential is less than negative 75 millivolts, the current moving through the open GABA receptor is negative. So positive charge is moving into the cell, and the cell is depolarizing. What we also see is that when the cell membrane potential is above negative 75 millivolts, the current moving through the open GABA receptor is positive, so therefore positive charge is moving out of the cell, and the cell is hyperpolarizing. So now let's apply this idea to the cell itself. So here is our postsynaptic cell, here is our GABA receptor. So the 2 GABA molecules are going to be bound to the GABA receptor, which will open the receptor. This will allow chloride to move through the cell. Now the effects of the open GABA receptor, as I said, is going to depend upon the membrane potential. Now when the membrane potential is less than the reversal potential of negative 75 millivolts, this will cause current to move into the cell, which will depolarize the cell. And when the membrane potential is above negative 75 millivolts, what's going to happen is that the current will move out of the cell, which will therefore hyperpolarize the cell. Now, this effect of the open GABA receptor is going to be the predominant effect in our body. And the reason why is because most neurons are going to be negative 70 millivolts. And that is going to be the resting potential. And since negative 70 millivolts is more positive than negative 75, then the current moving through the open GABA receptor will be positive. So therefore, positive charge will move out through the open GABA receptor, which will hyperpolarize the cell. So this is why GABA is often called an inhibitory neurotransmitter, because it hyperpolarizes the neuron, making it less apt to fire an action potential. Now, it's important to realize that other molecules besides GABA can bind to the GABA receptor. And this is because the GABA receptor has many different binding sites. Now, a particular binding site that it has is an allosteric binding site. An allosteric binding site is a site in which an allosteric molecule can bind. Now, in order to investigate this effect better, we have an experiment here with 3 different trials. And each of these trials are going to be measuring the membrane potential in response to the opening or not opening of a GABA receptor. Now, it's important to realize that all of these cells are going to be starting at a membrane potential above negative 75 millivolts. So when the GABA receptor is open, it's going to facilitate an outward current, so therefore it's going to hyperpolarize the cell, as we would expect. So now let's look at the trial 1. In trial 1, we're going to only expose a GABA receptor to GABA alone. So only GABA is going to be exposed to the GABA receptor of a cell. And what we would see is this. So what we would see is what we would expect, that when we expose the GABA receptor to GABA, it will cause the GABA receptor to open around here, which will facilitate an outward current, which will hyperpolarize the cell. And then once GABA starts to leave from the receptor, it would come back to the resting potential. So this is what we would expect. Now, there's another molecule that I'm going to bring up called a benzodiazepine. Now, benzodiazepines are allosteric molecules that can bind to an allosteric site. Now, an allosteric site is a site outside of the ligand binding site. And when a molecule binds to an allosteric site, it causes a conformational change that can either stabilize the open state or destabilize the open state. So let's take a look at what the effect of the benzodiazepine is upon a GABA receptor. So in order to understand this, let's take a look by exposing our GABA receptor to only benzodiazepines. So we're not going to be exposing the GABA receptor to GABA, but we're only going to be exposing it to benzodiazepines and looking at the effect. And what we would see is something like this. What we would find is that the membrane potential wouldn't change. In other words, the benzodiazepine did not cause the GABA receptor to open, so therefore it did not cause a hyperpolarization. So what we see here is that even though benzodiazepine is a molecule that can bind to the GABA receptor, it cannot bind to the GABA receptor's ligand binding site, so therefore it does not open the channel. So in order to see the effect of benzodiazepines upon the GABA receptor, we have to expose the GABA receptor to GABA as well. So in the 3rd trial, we're going to be exposing our GABA receptor to both GABA and benzodiazepines. So let's take a look at the effect. So what we see is that when we expose the cell to GABA, we see that the cell will hyperpolarize and come back to rest. But what you should notice here is that when we expose the cell to benzodiazepines as well, the relative hyperpolarization is greater in trial 3 than it was in trial 1. And the reason why is because benzodiazepines are allosteric modulators. They basically, when they bind to the GABA receptor, they cause the GABA receptor to be stabilized in its open state, therefore allowing more current to pass through. So this is basically summarizing to you what an allosteric molecule is. And this sentence is summarizing to you what benzodiazepines are. So benzodiazepines are positive allosteric modulators that help to stabilize the open state of a channel. This allows the channel to be open for longer periods of time when GABA is bound to the GABA receptor. However, benzodiazepines do not open the channel. They only stabilize the open channel. And they can only do their job when GABA is already bound to the receptor. So in order for benzodiazepines to work, you have to have GABA present as well. So now let's summarize what we talked about in this video. So we saw that GABA is a neurotransmitter that binds to the GABA receptor, and that the GABA receptor is pentameric and has 2 ligand binding sites. The GABA receptor, as we saw, has also allosteric binding sites, and when allosteric molecules bind to them, it causes a conformational change that can either stabilize or destabilize the open state. Now, GABA, as we saw, is permeable to chloride, and the reversal potential for the GABA receptor is negative 75 millivolts. We saw that when the membrane potential is below negative 75 millivolts, the open GABA receptor depolarizes the cell, and when the membrane potential is above negative 75 millivolts, the open GABA receptor will hyperpolarize the cell. Therefore, GABA is usually an inhibitory neurotransmitter, and it is the main inhibitory neurotransmitter inside the brain. And lastly, we talked about different allosteric modulators, and we see that benzodiazepines and another one, barbiturates, can bind to allosteric sites, stabilizing the open state when the GABA molecules are bound to the receptor, and it therefore increases the amount of current passing through the channel. Therefore, it increases the relative hyperpolarization of the cell when the cell is above negative 75 millivolts. So I hope this video helped you understand what the GABA receptor does and how it works. And I hope to see you in the next one. Good luck in your studies, and see you next time.